For our first lesson in grade 10, we're going to look at the number system. And an overview of this lesson is we're going to start with number sets. Then we're going to look at rounding off, which you've seen a lot before, but it's just important to revise that. And then something brand new, writing recurring decimals as fractions. And then finally also determining between which integers an irrational number lies. Okay, so for number sets, the first type of number that we see that we can get is natural numbers. And the very first thing you ever were taught in your life about maths was to count. And that is basically all the numbers that you use in counting 1, 2, 3, 4, 5, and it goes on like that. Alright, and then we get whole numbers. Now the set of whole numbers was created to include the number 0. So whole numbers is basically exactly the same as natural numbers, it just includes 0 as well. And then finally we get integers. Now integers includes all the whole numbers, but it also includes the corresponding negative numbers. So where we had 1, 2, 3, 4, and 5, we only also now have -1, -2, -3, and so on. Okay, so then if we're going to look at natural numbers in a bit more detail, natural numbers is an infinite set. That means that it goes on forever. So there are an infinite amount of numbers in the natural number set, and then it's composed of prime numbers and composite numbers. Now if you remember, a prime number is a number that is divisible only by itself and by 1. So a number as a natural number can either be a composite number or it can be a prime numbers. And prime numbers, example of prime numbers are 2, 3, 5, 7, and so on. Okay, and then also it can be written as a product of prime numbers. So if we have a composite number, this 240 is a composite number, and if we write it as products of prime numbers, we've got 2 to the power 4 times 3 times 5. A very important thing finally about natural numbers is just to know what the number line looks like. So it starts at 1 and it only goes into the positive direction, and then we have discrete values of 2, 3, 4, 5, and so on. Alright, next we're going to look at whole numbers. Now whole numbers, as we saw, is just a set created to include 0. So it's basically exactly the same as natural numbers, except it also includes 0 or starts with 0. And then finally we look at integers. Now integers are the set contains all whole numbers, as we saw, and as well as all the negative numbers. Okay, so the number line looks as follows. It goes into infinity, into the positive direction, and into the negative direction. And that is how you would then draw the number line if you were asked to draw, to represent integers on a number line. Okay, now the next type of numbers that we find is rational numbers and irrational numbers. Okay, so rational numbers can be defined as, it can be written in the form as a over b, where a and b are integers. Now this, all of this up here, this is just written in words. This is the mathematical notation of saying that it can be written in a over b, where a and b are integers. So if we have a number set, a rational number set, where x represents our numbers, then x is a fraction where we have a over b, and then a and b are elements of integers. This is just saying where a and b are integers, or where a and b are elements of integers. And then this final thing says that b cannot be 0, because if you look at b is the denominator, and we can never have anything over 0. Alright, so then another thing, if you get all the integers, as we saw, they are all also rational numbers. Now, if we look at a fraction with an integer over an integer, that would be like 3 over 5. We can even have a negative number like -3 over 5. Now, if we look at integers, let's say we have 3, then we can also write it in the form as a over b. We can write it as 3 over 1. So all your integers are also rational numbers. And then finally, if you have decimal places or a number that's in its decimal form, then you can identify a rational number by determining whether it is either terminating or recurring. And examples of that is terminating means like 0,316. And I can actually say that this is a rational number because I can write it as 316 over 1,000. Then it's also an integer over an integer. The other definition is recurring. So recurring means if I've got 0,5, for example, where the 5 recurs, 0,5555. We're going to see in a later section how to write that as a fraction. But for now, you can just accept that whenever you see a number where the decimals are recurring, then you can know that that number is also rational. Okay, then just to identify irrational numbers, we're just going to go to the opposite as what we just saw. These are containing non-terminating and non-recurring decimals. So a very common example that everybody would like to use or likes to use first is just pi. We know pi, if we put it into the calculator and press equal, we'll see that the value of pi is it's non-terminating and non-recurring. Let's actually do that. If I say pi and I say SD, you can see that these values, nothing is recurring here, and it actually goes on forever. The calculator actually just stops there because that's how many decimal places it shows. But this number goes on forever. So that is then the one and only definition for irrational numbers. And I think it's actually easier to check if it's an irrational number because you just check if it's non-recurring and going on forever. Then you'll know, okay, this is an irrational number. Right, now the next type of division we have is between real numbers and non-real numbers. Okay, now all the numbers we've handled so far, including all our rational and irrational numbers, they are all real numbers. Right, so it contains all the rational and irrational numbers, everything we've done so far. And then what does non-real numbers mean? Non-real numbers are actually numbers that does not exist. Okay, and there are two types of non-real numbers. The first type is when you have a negative number in an even root. So for example, if I say -3, if you type this into your calculator, you'll see that it gives you a math error. So this is an example of a non-real number, and it says even root. So even if we have like the fourth root of -3 or any negative number, you'll see that it is non-real. But if I take an uneven root, like if I replace this 4 with maybe 3 or 5 or 7, it is actually a real number, and you can confirm that on your calculator if you want to. Okay, so now a number divided by 0 is the second type. So if I have 5 over 0, this is also something that does not exist. You cannot have 5 out of nothing. So this one is the other non-real number. And once again, type it into your calculator and see if it works. And so these are the two non-real numbers. All other numbers are real and exist. Okay, so just to summarize everything we just saw up to now, we had natural numbers, we had whole numbers, and we had integers. So natural numbers was starting from 1, everything that you count with, and then whole numbers starting from 0, and integers, all the positive and negative numbers. So these three numbers, they do not have any decimal places. Okay, and all of these are included also in rational numbers. All three of these are rational numbers. Now, another thing you need to remember about rational numbers, it's these three. But then it's also if you have a fraction, you check it to see if the fraction is an integer over an integer, then you know, okay, this is rational. And if it's a decimal place, if it's a decimal, you just check if it's recurring and if it's terminating. Okay, and then for the rest of them, they are all irrational numbers. Now with rational and irrational numbers, they are all real numbers. Okay, so rather check from the non-real side whether a number is real or not real. So just ask yourself, does the number, is it like a negative in an even root, or is it over 0, if it's one of those, it's non-real. All the rest are real numbers. Now, this is the part where we're going to practically apply what we just saw. And before we start, I just want to show you a different method. I think you might have seen these in earlier grades. We have to classify this number as being which types of numbers. Now, normally you'd start from left and you'd say yes, no, but I'm just going to show you a method that I find easier. I normally divide my real and non-real as one section, and then I divide my rational and irrational as a section on its own, and then also these three types on their own. Okay, and then also I do not start from the left, I start from the right. I first ask myself, is it real or non-real? And if I want to see if it's non-real, I just ask myself, is it is it a negative in a square root, or is it over 0? And we can see if -5 definitely not, so this is definitely a real number. Now, rational and irrational, I divided in this section because it has to be one of them. You have to stick either rational or irrational. So unless this is non-real, then nothing is applicable here. But as long as this is a real number, you have to tick one of these. Alright, so and then for irrational, I just simply ask myself, is it going on forever? And there's no recurring going on. No, so then it must be rational. Okay, so we also know that integers are all the negative numbers, but whole numbers only positive. So these natural and whole numbers are not, -5 is not part of that number set. Okay, going on to the next one, we've got 0,8. Now, non-real means negative in a square root or in an even root or over 0. That is not, that is a real number then. Now, rational and irrational, is it going on forever? Yes, but it's recurring. So that means it is rational since it is recurring. Now, if you have a number with a comma or decimal place, then none of these are applicable unless it's like comma 0. But these values are only numbers that you basically count with. Okay, and then we have 70. Now, if you have something like this or anything more complicated, like not just the final number, just type it into your calculator. So we'll say square root of 70. Okay, and then just get the final number and work with that. Okay, so if we look at this number, it's not a negative in an even root or over 0, so meaning it is a real number, but we saw that it's not recurring and terminating, so it is an irrational number. Okay, and obviously there's decimal place, so this is not applicable. Okay, next up we've got 2,7. Now 2,7 is a real number, and then it is terminating, so it is a rational number, but because it has decimal places, it's not going to be a natural whole number or integer. And then for the next one, we've got a negative. Now we've got a negative in a even root, so that means this number is non-real, so that is non-real. And obviously if it's non-real, none of these would apply. We can just end there. And then finally, we've got the square root of 49. Now, once again, I hope you know that this off by heart, but the square root of 49 is 7. So the real number, yes. And then rational number. And then it is also 7 is an integer. It's a whole number, and it is a natural number. Okay, so that was then the number sets. Now let's just quickly recap rounding off. The question says in example 2, round off the numbers to 2 decimal places. Now when we round off to a certain type of or certain number of decimal places, we just want to keep, like 2 decimal places, we want to keep 2 numbers after the comma. That means everything else we need to cut off. But when we cut them off, we have to decide this last number. Is it going to be like remain 6, or are we going to change it to 7? And the way we determine that is we look at the number, the first number here. If this number is 5 or bigger than 5, it means that this will change into a 7. If it's anything less than 5, it remains 6. So since we have an 8 here, it's going to change the 6 into a 7. So this is then going to become 7, 4, 7. And that's all we do there. Now for the next one, we've got 1,895 to 4, and we want to cut off everything after 2 decimal places. And since this is 5, it's going to change the 9 into a 10. But this is a special case where this 10 is then going to change this into a 9. So this is just 1,90. I'm going to be safe and just say 90 when they ask for 2 decimal places. But I don't think 1,9 would be wrong. Okay, now we've got 3,564,216. So we're only interested in 5 and 6, but we have to just see, does 6 stay 6 or does it become 7? And since this is just 4, it's not big enough to change it into a 7, so it remains a 6. So it's going to be 3,56. Okay, that was it for rounding off. Now, moving on to writing recurring decimals as fractions. Okay, so this is a section where you have to pay close attention. This is new and it can be a bit daunting. This one is quite simple. Now, we saw that recurring decimals are rational numbers, and now we're going to show that we can actually write it in the form of A over B. So the first thing you do is we're going to work with this number. So let's give it a name. Let's say x is equal to, okay? Now the next thing I want to do is if there's one number recurring, okay? And if there's one number recurring, then we're going to multiply both sides by 10. If there's 2 numbers recurring, we're going to multiply both the sides by 100. And if there's 3 numbers recurring, which we'll see in the next example, then we're going to multiply both sides by 1,000. Okay, so since we have that one number is recurring, so you're going to say 10x is equal to, now if I multiply by 10, remember when you multiply decimal value by 10 or divide it by 10, if you multiply, the comma moves up. If you divide it, the comma moves back. So if I multiply by 10, then I get 5,555 and so on. All right, now we can subtract the 2. This is the next step. So 10x minus 1x, or just x, is 9x. And when I subtract these two, what's going to happen is that everything after the comma, because it's identical, everything after the comma just becomes 0. So if I have like 5 minus 5, it's 0, 0, 0, 0. Okay, so what we're left with is just simply 5, right? Then to get x on its own again, we just divide both sides by 9. And then our answer is 5 over 9. So here we can see that we can write this value as 5 over 9. And if you've done the sum, easy way to check yourself, just type into your calculator 5 over 9, press SD, and 5 over 9 equals, and then press SD, and then see that it's equal to 0,5 recurring. Okay, now in this example, we actually have 3 numbers recurring. So once again, I'm just going to give my number a name and say x is equal to. Now, if we have 3 numbers recurring, we have to multiply it by 3 zeros or 1,000. So this is going to be 1,000x equal to. Now, if I multiply it by 1,000, I move my comma up 3 spaces. So it's 1, 2, 4, comma, 1, 2, 4 recurring. Okay, so that goes on forever. Just a quick note, if I have 0,1, 2, 4, what this dots mean, it means that the number is recurring from the 1 to the 4. So if I should write this out, this looks like 1, 2, 4, 1, 2, 4, and 1, 2, 4. It just goes on forever like that. The other way I can write it is 0,1 to 4, where I have a line over all the recurring numbers. So this is just 2 methods of writing it, but it means the same thing. Okay, now what do we do next? We subtract. So I'm going to say 1,000x minus x is 999x equal to. So once again, if I subtract this with 0,124 recurring, the recurring decimals will cancel each other or equal to 0. So this is then, all I'm left with is 1, 2, 4. All right. Okay, so now I divide both sides by the coefficient of x. So x is equal to 124 over 999. Okay, and then that is our final answer. Okay, so now we have to do, or we have to write this guy in the form of a over b. So this one is slightly harder, and the reason for that is because we have some numbers here that are recurring. We can see 4 is recurring, but there's numbers here that's not recurring. So the first thing I'm going to do here is just to split them up, okay, into the non-recurring and the recurring. So this is going to be 0,12 plus, then remember you have spaces here, so plus 0,00 and 4 recurring, okay. Right, so now what's going to happen is this x is now, I'm only going to focus on the one that is recurring, okay, for now. Just going to say, okay, x is equal to 0,00, and then 4 goes on. Okay, now the next thing we need to do is we need to realize, okay, we want, what do we want? We want to be able to subtract two numbers where the decimal places will cancel. All right, so what I actually want is, I want my comma, and this is an easy way to remember it actually. You want your comma to be before the first number and after the first number. So you want your comma, let me just put this here. I want my comma to be there, and I want a comma to be there. Okay, so what do I need to multiply with to get my comma after the first decimal place? I have to multiply it 3 decimal places, so with 1,000. So I'm going to say, okay, 1,000 x is equal to 4,444 going on forever. And then I want my comma to be before the first recurring decimal, which means I'm going to multiply it with 100. So 100x equals to 0,444 going on forever. And then we subtract. So this will then give us 900x equal to, now the decimal places will cancel each other and we're just left with 4. So dividing both sides by 900, we get 4 over 900. And that is now our answer for this part, okay? Now, if we have 0,12, this is quite easy. If we have two decimal places, we put it over 100, 1 over 10 and 3 over 1,000. So this is just going to be 12 over 100. This is also something that you learned in primary school. And then plus, the value we got here was 4 over 900. Okay, and then we can just basically use the calculator and find the answer there. So this is 12 over 100 plus 4 over 900. Okay, so this gives us 28 over 225. So 28 over 225. Okay, now another thing which I said earlier is, if you have your final answer, there's a very easy way to check if it's correct. Now this is the calculator in its fraction form, and this is it in its decimal form. So if I say SD, it just converts it from decimal to fraction. So we can see that if I that my value here is identical to the value here, then I know, okay, my sum's correct. Okay, all right, so this is then the end of this one. Final section we have is to see between which two integers an irrational number lies. And this is quite easy, much easier than the previous section. So let's look at the perfect squares, okay? Because this is a square root. Now, between which two perfect squares would 20 lie? Like, let's list these. We have square root of 1, which is 1. We've got the square root of 4, which is 2. Square root of 9 is 3. And square root of 16 is 4, and square root of 25 is 5. Now, I wouldn't say write all of this out all the time. What would be good is maybe if you just write 1, 4, 9, 16, 25. And it's also good to know these off by heart, especially when you're going to do difference of squares, which we saw last year as well, to know these off by heart. Now we need to find the numbers where this number lies between. So if I look at these, I can see that 20 lies between 16 and 25. All right, so I'm going to write it as saying that square root of 16 is less than the square root of 20 is less than the square root of 25. All right, and then I'm just going to simplify this by saying, okay, the square root of 16 is 4, and then the square root of 25 is 5, and then that's that simple. It lies between 4 and 5 basically, but you start with the perfect square values. Okay, in this case we've got a perfect cube. So what are our perfect cubes? We've got, now this is how I'd recommend you'd actually write it out, even if you do it here at the bottom. We'll say 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 is 64, 5 is 125, and so on. All right, so if I want to find 35, where does 35 lie? 35 lies between 27 and 64. So I'm going to say, okay, the cube root of 27 is less than the cube root of 35 is less than the cube root of 64. And then I'm just going to simplify this. What is the cube root of 27? That is 3. And I'm just going to write this the same. And then that is 4. So the cube root of 35 lies between 3 and 4. Okay, now for this final example, here we have 2 and the square root of 12. So the first thing I'm going to do is just to get it into just going to get one number inside the square root. For example, I'm just going to take 2 back into the square root, which means it's 2 squared, which becomes 4. So if I just write that out, we get 2 squared times by 12, and then this becomes 48. All right, now let's write out our numbers. 1, 4, 9, 4 is 16, then we have 25, we've got 36, and then we've got 49. Okay, so 48 lies between 36 and 49. So this is then going to be the square root of 36 is less than 2, the square root of 12 is less than the square root of 49. So that means that the square root of 36 is just 6 is less than 2, square root of 12 is less than 7. So it lies between 6 and 7. Okay, so just to recap, we just wrote it as 48, just to get all the numbers inside the square root. We listed our perfect squares. We looked at our number and saw which numbers does it lie between, and then we write that our first number is less than our value is less than the second number, so between these two numbers, and then we just simplified as saying the square root of 36 is 6 and the square root of 49 is 7, so it lies between 6 and 7. Okay, so that was the final section, and that means we are done for the day.